All right, so in this video, we're going to take a look at some examples of some infinite sequences, and we're going to determine if they converge or diverge. And if they converge, we want to determine, of course, what they converge to. So in this first example here, you can see a sub n being our sequence. And if we're interested in what's happening at infinity, we're going to investigate the limit as n approaches positive infinity of the sequence given. And remember, we refer back to the sequence many times as similar to how a function would operate. So if this is what we want to investigate, you can see if we evaluate our sequence here at infinity, we would in fact end up with 1 raised to the infinity, which is an indeterminate form. So we would need to now move forward with manipulating this function to hopefully allow us to use L'Hopital's rule. So what we'll do here is something pretty similar to what I've done many times in the past. We know that we can view this guy as y equals. We can log it in order to bring down the n. So if you remember from a couple sections ago, when we do this, in order to get it into a form that we can use L'Hopital's rule, this would need to be the natural log of 1 minus 2 over n squared divided by 1 over n. So again, I logged it, I brought that down, and then I flipped it around to the 1 over n here, so that we can now view it as a 0 over 0 once we evaluate at positive infinity. Okay, so if you need to go off the side of your paper and work that out, feel free. So we'll go ahead now and apply L'Hopital's rule. And if I take that derivative of the numerator, I'm going to get a 1 over 1 minus 2 over n squared back times the derivative of the n side, which would give me a 4 over n cubed. And then in the denominator, that's going to be a negative 1 over n squared. Now, I would certainly want to clean this up a little bit before trying to evaluate again. So in doing so, you'll have a negative 4n squared over n cubed minus 2n. Now, this is one of these cases where you again could probably go ahead and simplify a little bit if you wanted to, or if you wanted just to proceed with another iteration of L'Hopital's rule, you could. There's a variety of ways to handle this. The easiest way I find is just to know that you're approaching infinity, you're bigger on bottom, so that of course this limit is going to go off to 0. So I'll mark this as 0, but don't forget, we did log it back up here, so we'll need to take e raised to the 0 in this case. So if we have e raised to the 0, we get a 1. So what we can say then is that the original sequence converges to 1. All right, so as you saw in the last example, there wasn't a whole lot done differently than what we would have done earlier in the course, only now, of course, we're dealing with sequences. In this example, though, we do have an additional component now to consider, but we do want to determine if it converges or diverges, so we'll go ahead and investigate the limit as n goes to positive infinity of the sequence given. Now, a couple things to pay real close attention to here. You can see that this part of the sequence right here, this is by itself an alternator. This is only going to change from 1 to negative 1 based upon n being even or odd. So if we really think about this, if n is an odd number like 1 or 3 or 5, then this numerator goes to 0. If n is an even number like 2 or 4 or 6, then this guy goes to 2. So in reality, this function, this sequence is bounded. The smallest it could ever be would be 0. The biggest it could ever be would be 2 over root n. And so by bounding it as I have here, now it's probably going to jump out at you that possibly we could use the Squeeze Theorem to evaluate that limit. Since the limit is going to positive infinity, this limit would go off to 0. So that limit goes off to 0. Since this is already a 0, of course, it's 0. Therefore, what sits in the middle also has to go to 0. So we can then say, by the Squeeze Theorem, or a sandwich theorem sometimes it's called, the limit as n approaches positive infinity of a sub n converges to 0. Converges. And so in the last example we saw where we could use L'Hopital's rule on sequences, it's perfectly reasonable. In this example we see that we could still use the Squeeze Theorem as well, and we just have to of course be a little bit clever in our approach. Okay, so now we'll take a look at another example where this one has an alternator in it as well. And this guy, remember, this is going to only change between 1 and -1, depending on what the exponent is. So in a problem like this, knowing what this does, I'm just going to kind of ignore it for a second. And let's go ahead now and investigate the limit as n approaches positive infinity of n over 2n plus 1. Now we know by a variety of different ways to solve this, we know that this limit goes off to 1/2. And so does the sequence converge to 1/2? No, unfortunately not. What's going to happen is it's going to bounce around from -1/2 and 1/2. That's because I didn't take into consideration the alternator when I did this. So at infinity, it'll hit 1/2, but it might be positive or it might be negative. So it's just going to bounce back and forth to those two quantities. Since it's going to bounce back and forth, we would then have to say that the original sequence diverges. So since we don't land on a number, in this particular case, that sequence would diverge. All right, so in this example, we'll approach it the same way with a limit as n goes to positive infinity, 2 minus -1 over 2 raised to the n. And so in a problem like this, again, we're trying to take the overall limit, but I would certainly take advantage of being able to rewrite this. For example, this could be 2 minus the limit as n approaches positive infinity. And then I'm also going to go a little further and do a -1 to the n times a 1 over 2 to the n. Now, again, what I've done is essentially just distributed the limit. The limit of a constant is a constant. Then I went in there. That negative is right here. I split up the numerator and denominator both to the nth power. So there's my -1 to the n times 1 over 2 to the n. Now in doing this, it's going to make this limit much easier to compute. I again know that this is only going to change from pluses to minuses. That's all it's going to do for me. So I'm going to focus on this limit right here. So at infinity, this limit goes off to 0. So 0 times this is going to be irrelevant. Therefore, that whole part goes off to 0. And of course, leaving us with our final answer then of 2. So then we could say that the original sequence converges at 2. Now, as you saw in the last couple examples, it's all about the limits as n goes to infinity. Be creative, how you solve these types of limits, how you evaluate these limits, but really focus in on just the parts that are necessary in order to determine convergence versus divergence.